Okay, let's start. So we'll continue our discussion on divide and conquer. We're looking at this convex hull problem, which is you are given a set of n points in the plane xi, yi. You are given their x coordinate, y coordinate, and what we want is the smallest polygon or convex polygon containing all points in P. So you know the meaning of convex and concave, right? So convex means if you draw a line passing through two vertices, it should strictly lie inside the polygon. Concave is the opposite of that. Okay. So this is what we were looking. This is called the convex hull of P. All the points are strictly lying inside or on the polygon. Okay. And normally we represent this convex polygon as a circular doubly linked list. Right. So there will be a link from A to B, B to A, B to C, C to B, and so on. Okay, this is how it looks like. So you have to use a doubly linked list to output this convex. And we did see some one naive brute force algorithm. How do you decide whether AB is an edge of the convex hull or not? We just see that all the points are on the same side of this edge segment AB. Okay, and this you can do for all segments connecting a pair of points, that all the other points are on the same side of the line segment. And how do we check whether all the points are on the same side of that line segment? Is by taking cross product. Okay. So how many pairs of points do we have? There are n square many, or big O n square. So you can choose 2 points in n choose 2 ways, and that is roughly big O n square. And you can do the cross whether a point is on the left side or right side. You can check by computing the cross product. You can do it in constant time and check for all n minus 2 points, ignoring these 2 points. Okay, and that turned out to be big O of n, right? So for each pair of points, we can check whether all the other points are on the same side of the segment in big O of n type, and there are n square many such pairs. So overall, the running time is big O of n cube. Okay, the running time is big O of n cube. Now, obviously, we want to do better than this trivial algorithm. So we are going to do something different now. And what we started, we use our strategy divide and conquer. So there were some ideas suggested, but most of your ideas are using the iterative approach. But here we are interested in divide. Okay. So for this problem, many ideas are both. One using divide and conquer, one using sort of iterative idea. But here we'll focus on divide and conquer. So how do we divide? We divide the points into two roughly equal size sets. Let's call this sets P1 and P2. Then in the conquer step, we find the convex hull made by P1, convex hull made by P2, and then we need to combine these. Right? We want to merge these two convex hulls. Okay. The simple strategy which we have. So let's say we had this set of points. We look at their x coordinates and find out their median. We already saw median finding linear time algorithm before of n. So using this, you can find this vertical line which partitions this set of points into roughly two equal halves. Okay. On each half, we found the convex hull. Okay. Here, the segments in black, they are our convex hull of P1. Similarly, we have this convex hull of P2. And now the more interesting part is, notice that this cannot be the convex hull of the entire set of points, because all the points in P2, they are strictly lying outside. Similarly, this cannot be the convex hull for the entire set of points, right? Because all these points are outside this convex hull. And therefore, we need to sort of merge these two convex hulls to get a new convex. Okay. So how do we merge these two? So any ideas? How are we going to merge?
Sir, can we connect the topmost y coordinates of the convex hull of P1 and convex hull of P2 and similarly the bottommost?
Yeah, so that's the idea. And so you see why the topmost and bottommost are always going to be contained, right?
Yes, sir.
Because let's see, we start with this two things, right? This is the rightmost part in this P1, and this is the leftmost part in P2. So why is this not an edge of the convex hull? Because there are points on both sides of this edge. Some points are below this segment, some points are above. Okay. Once you take the highest point, which is having the highest y coordinate, you are guaranteed that all the other points in P1 are below this thing. Right? Similarly, all the points in P2 are below this. So we can be guaranteed that this is an edge in the convex hull. And what we want to do is, how do you find this is what we call as the upper tangent, and this is what we call as the lower tangent. Okay? By the same logic. Okay? And even before that, uh, let's see a trivial merge step. Okay. So we have these two convex hulls, and we want to find some edges of the convex hull which are going from P1 to P2. Okay. And how do we check whether this is an edge of the convex hull? All the points should be on the same side. Again, we use the cross product thing, and yeah, you can easily find that. So the trivial approach is you pick all points here and pick all points here. For every such pair of points, you check whether it is an edge of the convex hull. Right? And why is it an edge of the convex hull? All the points should be on the same side. Okay. So how many such points do we get? So there are roughly n by 2 points here, n by 2 points here. The total number of pairs will be n square by 4, and that is big O of n square. So there's a trivial big O of n square merge step for this step. It will take big O of n square time, trivial. So now what is the recursion we'll get? Let Pn be the time to compute convex hull of n points. This will be twice Tn by 2. There are n by 2 points on each side plus big O of n square. And so you'll get the time complexity as big O of n square. And obviously we are not satisfied with this. So from n cube we went to n square. So here is another idea. Let me pick the point with highest x coordinate here, and let me pick the some point here. Okay, maybe it is the one with the lowest x coordinate. Okay, so we found that this is not an edge of the convex hull because some of the points are above this line segment, some of the points are below this line segment. So then how do we find these highest things? So one idea is that, of course, you can sort by the y coordinate and just check. But here is another idea, which is to look at the line segment where it intersects the dividing line, this dividing line, okay, this vertical line. So let's say it meets here. Okay. And when you want to find the upper tangent, notice that the line connecting this intersects this middle line at the highest point. Okay. It intersects it here. This line segment intersects it here. This line segment intersects it here. So we want to find the line which is intersecting this middle line at the highest point. Okay. And how do we find that? That's the main question. So we started with these 2 points, let's say. And then you process the points. Let's say we moved from clockwise direction here and anti-clockwise direction here. Okay. And then you see, let's say we moved in the clockwise direction here. So this was definitely not a line segment of the convex hull. You look at this point where it is intersecting this middle line. So it's below this previous intersection point. So this guy we can reject. Okay. And you keep on repeating this unless you find the highest point. Okay. So this is a simple big O of n procedure to find the highest point and the lowest point. So we find this upper tangent, we find this lower tangent, and that is enough to find the combined convex. Okay. So this is just a pseudocode. Let P be the rightmost point in convex hull of P1, Q be the leftmost point in convex hull of P2. And what we want is Yeah. So we look at the successor point of P, which is the next point after P, and the previous point of P, which is the point before P in convex hull of P1. And we check whether the successor of P or previous of Q lies below PQ. If successor lies below PQ, then P will be changed to successor of P. Otherwise, Q will change to previous. So this is because we looked at one set of points in clockwise direction, the other set of points in anti-clockwise direction. Finally, when we can't make any progress, we just return P. Okay. So what's the running time? This is for the divide step. We divide into two sets of n by 2 points, found the convex cells. So 2t n by 2. And we take linear time for merging these two convex cells. Okay. Solve this recurrence. You have solved it already many times. You will get big O of n log. So we get this big O of n log n time algorithm, which is good. And it is almost the best known for all possible algorithms. Okay. So here is just a description. If n is less than equal to 3, right? If there is one point, that point itself is the convex cell. If there are 2 points, you just connect those 2 points. And if there are 3 points, you just draw the triangle made by the 3 points. So you can return this convex cell trivially in constant amount of time. Otherwise, we divide P into P1 and P2. Okay. So P1 is n over 2 and P2 is whatever, n over 2, roughly n. Right? This step you can do in n log n time because, of course, median you can find in big O of n. The other approach is just sort those 2 points according to their x coordinate, and we would just divide these points according to their x coordinate. Half the points go into P1, the other half goes to P2. Recursively compute the convex hull of P1 and the convex hull of P2. Combine these two formulas. Okay. So we get n log n time algorithm here. Yeah. And this is basic divide and conquer algorithm. So initially our naive approach, which is by brute force, we got n cube time complexity. By others divide and conquer, we reduced it to n square, and finally we come to n log. Okay. And notice that this n log n is better than n to the 1 plus epsilon for any epsilon. Okay, because log n is strictly less than n to the epsilon. So this is good. This is one of the best algorithms for convector. This is currently known. Okay. So there have been some other approaches also. If you don't want to use divide and conquer, what do you do? So there's one algorithm which is known as the Graham scan. Okay. It also runs in big O of n log n. Okay. So what is Graham scan? You are given this set of points. Okay. And his idea was the lowest. Forget this divide and conquer. We are not dividing. We are looking at all sets of points. Okay. And he looked at the lowest y coordinate point. Okay. And his claim was the lowest point should always be contained as a vertex in that convex. Okay. And then he arranged these vertices in some anti-clockwise order. So how do you find the next point? If I give you one point, you know the lowest point is always contained in the convex hull. How do you find this point? What is so special about this point compared to other points? Yes, tell me.
Sir,
Yeah.
sir, if we have one point which is we know that it is in convex hull, then we can
Okay.
find adjacent 2 points to it by taking slope of all points, and
Yeah.
the maximum slope and minimum slope of containing points
Yeah.
are adjacent to it.
Yeah. Exactly. So that was the idea in Graham's cat, is that he found the next point by taking the minimum slope. Okay. The slope you can find by dot product with the x-axis and or whatever cross product or dot product with the x-axis. And exactly this was the idea, and then he found the next point and so on. Okay. So it requires a sorting step. You need to sort these angles, and that you can do in n log n time. Okay. So this was Graham's cat, and a very similar idea was also used. Is known as the gift wrapping algorithm and Jarvis mark or Jarvis mark. Okay. This is not the Jarvis, some other Jarvis. And yeah, so what Jarvis did was, okay, let me go back and okay, yeah. So here we took the lowermost point. Jarvis' idea was to take the leftmost point. So it just shift of coordinates. Okay. Instead of y-axis, you're looking at the x-axis. Okay, and he took this point. Okay, the next point which is connected to it, you can find in big O of n type. Just check whether all the points are on the same side of this point. Okay. And again, the same thing you repeat. So each of these edges take big O of n time. Okay. And let's say there are h many edges. Okay. The overall algorithm runs in big O of n times h. Okay. So big O of n times h, where h is the number of points on the convex hull. So this is good than n log n in certain cases. If the convex hull has few sides, less than log n, then you'll prefer this algorithm. But if the convex hull has many points, what is the worst case time complexity? All n vertices can be a vertex of the convex hull, right? So the worst case will be n squared. We also saw two divide and conquer things, big O of n square, big O of n log n. And there is another chance algorithm which runs in n log h, which is just combination of the first two, Graham scan and Jarvis smart. So here we divide it into two parts. He divides into many different parts. Okay. And somehow is able to get n log h. Okay. Yeah, that's the end of convex hull and also our primer on divide and conquer. So if there are any questions on this, let me know. Okay, if there are none, we will end our. We have tried to cover as many examples on divide and conquer, and it is a useful approach, very useful approach to give fast algorithms. You can keep on practicing some other examples. Try to devise divide and conquer things, but it doesn't work always. Uh, Only for some specific problems. And what we want to do is now to look at this greedy algorithm approach. So how does this greedy approach work? So it is sort of an iterative procedure. We construct a solution by considering one step at a time. Okay. So your algorithm is essentially a sequence of choices. You want to make some choice at every step. And here the idea is it chooses the locally best solution. Okay. So you repeatedly choose the locally best solution and hope that it gives a globally best solution. Okay. So certain places where divide and conquer doesn't work, you can always use greedy algorithm. Uh, Repeatedly choose the locally best solution so that it gives you the globally best solution. Okay. And of course, there are some advantages of this approach. There are some drawbacks of this approach, and you would like to see both of them. Okay. So, what are the advantages? It is easy to describe. Okay. So, obviously, it is easy to describe because you can easily make those choices, which is the locally best solution, and you can also implement it efficiently. Okay. What are the drawbacks? It is choosing the right greedy approach is hard. So as we will see, many approaches which look obvious to us, there will be some pitfalls or falsities in that. So choosing the right greedy approach is difficult, and correctness is sometimes very difficult in this greedy. So it's hard to verify whether the algorithm is correct. So some things might look very intuitive, but proving that it is correct, that is the more difficult part in this greedy algorithm section. So it is hard to verify. And the first problem which we'll look at here is it's called the activity selection problem. Okay. And there are different names: interval scheduling problem, maximum independent set with intervals, and so on. Okay. So the problem is this: you are given n jobs, j equal to j1 to jn. For each job, we have got a start time and a finish time. J1 as start time S1, finish time F1, J2 as start time S2, finish time F2, and so on. Okay. And we say that two jobs are compatible if they do not overlap. Okay. So ideally, we want the finish time of J1 to be less than the start time of J2. In that case, we say that they do not overlap. And a feasible solution is to find a subset of mutually compatible jobs, and you want to maximize the number of such jobs. Okay. So there are many analogies to this. This is how it looks. Let's say this guy's start time was 0, this guy's finish time was 3. So you can think of it as lectures, right? Some lectures start at time 0 and at time 3. 3 to 6, there is another lecture. 4 to 8, there is another lecture. And so on. So obviously, two students or a faculty cannot be at two different lectures at the same time. So we want to find the maximum number of lectures which do not overlap with each other, right? So let's look at this 1 and 4. Uh, these these do not overlap with each other. This is from 9 to 12. This is from 5 to 7. Okay, so there is no overlap between them. And this is what we call a compatible set of lectures. And what is non-compatible is start from lecture 9 to 11 and get this thing. This is from 10 to 14. So there is some intersection happening here. These are not compatible. And our goal is to find what is the maximum number of compatible jobs without any overlaps. Okay. So in this case, it turns out to be 4. 1, 2, 3, 4. And we want to schedule these lectures so that there are minimum number of overlaps. What is the maximum number of lectures without any overlaps? That is our problem. Okay. And obviously you can see that some divide and conquer will not work here because you don't know which to take first. So usually where you have to make a choice, greedy is the first strategy you will look at. Okay. And let me just please this. Okay. So this is known as the activity selection problems. Let's say we have these lectures, one from 2 to 3, 2 to 5, 4 to 7, 1 to 8, 5 to 9, 8 to 10, 9 to 11, 11 to 14, 13 to 16. Okay. And we want to find the maximum number of these lectures without any overlap between them. So what is the maximum number you can find? Yeah.
Here, would the intervals would be given on which time the jobs can be done?
Sorry, your voice was low. Didn't hear it.
Sir, my question was, are the
Are we? Are the intervals in which the jobs can be done given? Yeah, you are given these intervals 2 to 3, 2 to 5, 4 to 7. And 1 to 8. So these intervals are fixed. You have to start this job at 1 and finish it at 8. So yeah, what is the maximum number of jobs without any conflicts or overlaps? Job that ends as early as possible. Okay. So yeah, tell me, what's the answer here? How many jobs you can schedule here without any conflict?
Sure. 4.
4. Yeah, you would have seen this already. So which ones are the ones we want to pick here? Maximum number of activities which can be run without any conflict. So one solution is, again, we apply this brute force thing, which is consider the set of all possible subsets of activities and just check whether they are conflicting or not. Okay. Find the maximum size of a subset without any conflict. So if we are given some n jobs, what is the maximum size? How many subsets are there? 2 raised to n. Either you put an job in that subset or not. There are 2 choices for every job, and there's 2 raised to n. And we want to find the maximum size of a subset without any conflict and check for conflicts in constant amount of time. But anyways, this is an exponential time algorithm, and you want to do better using this 3D solution. You want to make some locally optimal choice at every step that leads to a globally optimal solution. Okay. So I'll just show you first some approaches which do not work. One thing you could do is select the activity with the minimum duration. That is an obvious thing to do. Okay. So you are given the start times, you are given this finish times, and you find the duration of this. So this will run for 1 hour. Let's say this runs for 3 hours, 7 hours, 4 hours, 2 hours, 3 hours. So if you want to schedule the maximum number of things, you will ideally pick the one with the smallest running time, right? So you could pick this one first. Okay. You pick this activity 1, and then you can't pick 2 because it is conflicting. You have one thing on 2 to 3, you cannot have another thing on 2 to 5. So D3, again, there is activity 3, there is no problem because this is from 4 to 7, this is from 2 to 3. Okay. What is the next you will pick? Activity 4, again, there is a conflict. This is from 1 to 8, 2 to 3. Activity 5, you can't pick because this is from 5 to 9, this is from 4 to 7. So you have to pick activity 6 next. 8 to 10, there is no conflict with anybody else. Okay, so you have 3 things. One is from running from 2 to 3, 4 to 7, and 8 to 10. 7 you can't pick because it is conflicting with 6, 8 to 10, 9 to 11. So you'll have to pick 8. That is from 11 to 14. And again, there is no conflict, so you can pick this 8, and 9 is conflicting with 8. Okay, so this is one thing. But unfortunately, it doesn't work for all cases. Right? The shortest duration, if you look at just the shortest duration, this is not going to work for everything. And here is a failure case. Let's say we are given the start times 4 to 6, 1 to 5, and 5 to 10. Okay. And what's the duration? 4 to 6 runs from 2 hours, 1 to 5 runs for 4 hours, 5 to 10 runs for 5 hours. So if you go by duration, you will pick this 4 to 6 job first. Then you can either pick 1 to 5 or 5 to 10 because both of these are conflicting with the first job. Okay. So in this way, you can pick just 4 to 6. But obviously, there is a better one. You could pick 1 to 5 and 5 to 10. So there are some cases where the shortest job is not going to work. Another approach is select the one with the smallest start time. Okay, the one which is starting first, we pick that job. Correct? And yeah, why this won't work?
Sir, if there is any activity which has very large duration and
Yeah,
it starts from t is equal to 0, then
yeah, exactly. So for instance, here is an example: 5 to 19, 6 to 8, and 10 to 12. You look at the smallest start time, you'll pick 5 to 19, but then you can't pick both of these. Okay? So the better approach is 6 to 8 and 10 to 12. So yeah, it is a good practice to practice such things, find counter examples for various approaches that will help you master the greedy algorithm. Okay. And so we decided, okay, let's pick the one with the smallest finish time. Okay. And it does work uh, without fail at for all cases. Okay. But proving that is a bit difficult. Okay. So initially J is the set of all jobs, and let me just, yeah. So initially A is empty. We don't have any jobs yet. Okay. We choose the job that has the smallest finish time. Okay. So smallest thing you can compute in big O of n, that is just the minimum. And we add this job to A. Okay. Then what to do? Delete all jobs not compatible with J. Check for overlaps and delete all jobs which overlap with job J. That takes big O of n time. Smallest finish time also you can check in big O of n time. And this procedure runs for big O of n many steps. Okay. So what's the runtime? It's big O of n squared. And obviously we want to improve upon it. But first, uh, we need to formally prove that, uh, let's say this was the output given by our greedy algorithm. It's A1, A2, A2. Started with the smallest finish time. A1 had the smallest finish time, then A2, and so on. And let's say this was the optimal solution, that the maximum you can have is M. Now, how does K and M compare? Okay. So let's say the solutions which we have are, they are sorted by their start time. Okay. A1 has the first start time, A2 has the second, AK. Okay. So one thing you can definitely say is K is strictly less than equal to M, because M is the optimal, so M has to be the maximum. So K is less than equal to M. Okay. But what we want to show is that K equal to M. So how are we going to prove that? So we will prove this via uh, using the specific property of our greedy algorithm. So for every I less than K, AI finishes not later than OI. Okay. So why is this the case? Because we sorted the job by our finish time. The smallest finish time comes first, then the next, and then the next, and so on. So it is clear that AI will finish not later than OI using just the property of our algorithm. And yeah, we want to use this observation to show that if K is the number of jobs here, M is the number of jobs here. So how will you show that K equal to M? Yeah, tell me. Yeah, thanks for letting me know. So the proving the correctness is usually very difficult. Uh, it to use many things. uh, so what do you know in this setting? Is that once we arrived at this solution A1, A2, AI, we know that AI finishes not later than O1. So A1's finish time is less than O1, A2's finish time is less than O2, and AI's finish time is less than O1. And what else do you know? Is that we couldn't have picked any other job after this. There is no AI, right? Because that just follows from this property. And now we want to show that K should be equal to this M. So obviously K is greater than M. That is not possible because K is the number of jobs we got using our algorithm and M is the highest number. And what we do know is that AK finishes not later than OK. So let's say that in the optimal thing, we have at least K plus 1. There could be more than that. And what we do know is that OK plus 1 is compatible with OK. So does that give you any clue here? How will you prove that this OK plus 1 does not exist?
Sir, job K and K plus 1 will intersect.
K and K plus 1 will intersect.
If OK plus 1 is starts before AK.
Yeah, starts after AK. Yeah. So then you could have added this, and that is a contradiction to our grading. Exactly, that's the idea. So K plus 1 can be included in A, and we could have obtained the bigger solution here, and that's a contradiction. Okay. Yeah, exactly. That's the idea here. K equal to M. So yeah, we got an n square type solution, and obviously you want to do better. You want to reduce the time complexity to n log. So here is another efficient algorithm. Sort the jobs by their finish time, sort the start time in array T. Okay. So we process jobs in increasing order of the start time, and then iterate over this array T to find the first index I such that Si is greater than the finish time of J. Okay. And so the main things are sorting here. They are sorting by their finish time and start time. Okay. So you can do this in n log n time. Okay. So the idea is to use some kind of priority queue where you can do these things. So what will be the key of your job? It will be just the finish time of this. So we'll see that idea later to use some clever data structure to make this running in log n time. Okay. Okay. Are there any questions so far on this problem? Okay. If there are none, we'll move on to the next thing. So it's called the interval partitioning problem. Okay. Again, we have the same thing. We have a set of n jobs, J1, J2, Jn, where each job has a start time and a finish time, Fi. So again, we have these n lectures. We are given their start time, we are given their finish time. And we want to partition these jobs into k sets, where each set of jobs are mutually compatible. Okay. So let's say you are given this set of jobs here, J1, J2 up to J10. And again, the same thing, but we want to create a partition such that each set there is no conflict. And we want the minimum number of such sets. Okay. So let's say I picked J1, J6, J9 in one, J2 and J8 in another, J3, J4, J7 in another, J5 and J10 in one. Okay. So this is a schedule with 4 sets. So what do you think? Is this the best you can do?
But these sets are not mutually compatible. J5 is overlapping with J4.
Yeah. So that is fine. But inside this set, I want, so you can think of it this way. So I want to schedule lectures in certain classroom. Okay. And one thing is I can have lectures running parallelly in different classrooms. And I want to ask what is the minimum number of classrooms I need for scheduling this lecture?
Okay, sir, means each set means within each set every job should be compatible. And
Yeah.
it is not necessary that every set is compatible with another set.
No, no, we don't need that.
Okay, sir. Okay, sir.
Sir, here we can uh, do this for k equals to 3.
Okay. So what do you suggest? How should
Sir,
we put this?
from first two sets that are J1, J6, J9 and J2,
Okay.
J8, we
Yeah.
will replace J1, J2 in both sets. So
Okay.
J2, J6, J9 and J1, J8.
Okay.
So in set J1, J8, J5 can be included,
Yeah.
and in set J3, J4, J7, J10 can be included.
Yeah. Sure. Yeah. That's the exact thing. And you can have a schedule with 3 sets. Exactly the same idea which you was talking about. Okay. So the question is, how will you find the minimum number of such sets? I give you all these things and start times and finish times, and you want to use the minimum number of sets.
Sir, we can choose the one which finish as late as possible.
One which finishes as late as possible. Okay. So is that going to work in all settings? Sorry, your voice was low. Okay. So we want to formally prove that this schedule with 3 sets is the best possible, right? Why can't you have 2 sets? Just 2 sets.
Sir, for every interval of time,
Yeah,
maximum number of intersection of jobs are 3.
yeah,
So
yeah, exactly. And so we want to do 2 things. One is that we look at maximum number of intersections at some point. Here there are 3. Okay, can verify that. And the next thing is we want to give an algorithm for constructing this schedule with 3 sets. Okay. Yeah, these are the applications of this and at least how many classes we need. So we will look at the maximum number of intersections here, and that is what we call the depth. Okay, depth of J. Okay, and yeah, that is what we call the depth of J. In this case, it is 4, right? And we want to construct this schedule. Okay, of course. So here is one approach. You want to design a greedy algorithm for this forces. So let me just there's some disturbance happening maybe. So I don't know how to mute these things and something here.
हाँ भाई बोल.
Yeah, okay. So we'll use this greedy template, which is consider the jobs or lectures in some order, which we want to fix, and assign each job to an available classroom. We then allocate new classroom if no other classroom is available. Right? So one idea is we could use the same thing, which is uh, look at the finish times. This is what we did when we wanted to maximize the number of classes without any conflict. Okay, so that seems like a very natural strategy here, because if you had the maximum number of jobs in one classroom, then obviously the partition will have fewer sets or fewer classrooms. But unfortunately, it doesn't work. For instance, look at this example. You could have the finish time of J1 is first, J2 you couldn't have picked, and there is option between J3 and J4, but J4 has the first finish time, so you pick J1 and J4 in one thing, J2 in another, and J3 in another. But if you look at the optimal, it is different. J1 and J3 in one classroom, J2 and J4 in another. Okay. So this earlier finish time is not going to work. And yeah, so we need to do something else. The other idea is we use the shortest job first. Like, which is the shorter one? We put that. So is this going to work? Shortest job. So it's sort of the same example as we had the activity selection problem. Right? This strategy did work here. So take it as homework. Can you construct a counter example for like this? Okay, shortest job per lecture. And even fewest conflicts. Okay, you could have pick the one with the fewest conflicts. So all these three don't work. And next class we will see a counter example for each of these. Okay, but try to figure it out on your own. Okay, and what in fact does work is we pick the jobs in increasing order of earliest start time. Okay, consider the jobs in increasing order of this start time. Okay, so what is our algorithm here? We sort the jobs in increasing order of the start time. The depth is 0 here. For I from 1 to n, we check whether the ith job is compatible with some classroom, then schedule ji in such a way. Okay. Else we allocate some new classroom and increment the depth by 1. All this we can do in constant time and just return that schedule here. So what's the running time here? This loop runs in big O of n time. Sorting takes n log n time. And inside the loop, you are doing big O of n work. Okay. So overall running time is n squared. So you know how the algorithm works, right? So let's say we are given these jobs here and we process the jobs in increasing order of their start time. Okay. So just increment those things and yeah, schedule them. Okay. So let me just show you one example here. Yeah. So how will you do it here? So we'll look at the jobs in increasing order of their start time. First, we'll process J1, put it in some classroom. What's the next one? J2. But this obviously intersects it, so J2 has to go in some other classroom. Then comes J3. J3 doesn't intersect with J1, so you put it in the same classroom as this. And then comes J4. So J4 doesn't intersect with J2, so you put it in that classroom. Okay. So this is how you get the optimal thing. And yeah, it's sort of counterintuitive, but we want to show how this early start time strategy works. Why does it work, first of all? Any ideas? Why should early start time work? So the main challenge in greedy algorithms is not to devise this particular algorithm, but coming up with a good greedy strategy and then proving the correctness part, whether your algorithm is indeed correct. So why is the earliest start time going to work? Okay, so we are almost, time is almost up. So just think about this and try to come up with a proof that uh, earliest start time indeed does work and how you are going to prove it. Okay. So yeah, any questions?
Hello, sir.
Yeah,
Sir, in convex hull problem,
yeah,
there was one algorithm of which have order 10 times h, where h is
yeah,
number of points
yeah,
on convex hull.
yeah, yeah. Yeah, this one, gift wrap jargon.
Yeah. So, sir, let's take an example in which there are n number of points total. N by
Yeah,
2 are on convex hull and n by 2 are inside.
okay.
Now, sir, according to this order of it should be what should be its order?
N square, right? If n over 2 points are there on that convex hull, so this is just n square by 2, which is n square.
So, sir, for any case it will become n square.
For any case, so for some cases, let's say there are only constant number of points on the convex hull. Okay,
Yes,
so
sir.
it is quite possible, right? You can have just a triangle such that all the other points are inside the triangle. So in some cases you will get a linear time thing, but some cases obviously worst case will go up to n square.
Okay, sir. So if h is constant, then only we get order of n.
Yeah, yeah.
Sir, but if we are given points, then how can we decide whether h will be sufficiently small or not?
How will we decide whether h is
As a,
sufficiently small or not?
yes, sir.
Yeah, a priori you can't decide whether h is sufficiently small or not.
Sir, but if we know the distribution of the points, then if the
Yeah,
distribution, if the distribution is very dense, then we
yeah,
can say that the h will be sufficiently small because it will be a smaller convex hull and so smaller points will be needed.
yeah, something like that. Yeah, it's an interesting problem. How will you decide whether uh, number of points on the convex hull is sufficiently small or not?
And sir, if the points are scattered over a wide range,
Uh,
then then there are more chances that the point is on boundary.
yeah, that is an excellent question actually. Uh, yeah, something about the distribution you want to. Okay. So for constant, you can always do it because uh, no, even for constant, it is difficult. How are you going to decide if convex hull has at most 3 points?
Sir, for that we need to traverse and find out the complex fuzzy itself.
Yeah. Yeah, it looks
Sir,
a difficult problem at least. Yeah.
sir, then I think that the distribution should be known beforehand.
Yeah. Otherwise you can't. So
Otherwise, it
that is
will
why
not
we,
be.
yeah, yeah. We can't decide which is the best algorithm among these.
Otherwise,
So
it will
normally
be.
we, yeah,
Means otherwise it will be inefficient to find out whether whether the h is constant or h is sufficiently small or not. It will be inefficient,
yeah,
I think.
yeah. Yeah, let me think about this for some time. Uh, I'll see if, but mostly we use this n log n thing. It is the more safer option instead of first deciding whether h is small or large and then choosing which algorithm to apply. In
Yes, sir.
practice, we use this n log n algorithm. This gram scan is practically used most, or the divided conquer, which you saw. Okay, if there are no more questions, let's stop here. We are already over time.
Sir,
Yeah,
sir, one algorithm was having complexity as order of 10 times log h.
yeah.
So can we say that it will be always less than gram scan means this will be
Okay. Yeah, that is true.
so why
This
don't we use
chance
this
algorithm.
as
So yeah, you can use it, but implementing it is slightly more difficult or complicated. And, yeah, I think you will have an exercise on convexal in the lab assignment. Yeah, you can try all these approaches.
okay sir, thank you.
So it's again, it is a combination of these two, gram scan and Jarvis match. So what we do there is split the points into various sets, and in some of the sets you apply this gram scan, some of the sets you apply this Jarvis match, and that is how he got n log h. So if you are anyways using this two algorithms, you better use this gram scan. So that's the idea. Okay, let's stop here now.